In this section, we'll look at the fundamental theorem of calculus. So, up until now, we've had two seemingly unrelated concepts: the concept of the indefinite integral, and the concept of the definite integral. And the fundamental theorem of calculus, or one part of it anyway, tells us how these two things are related. So remember, this symbol or this notation told us to do something with antiderivatives. And this notation had something to do with area underneath curves. So what the fundamental theorem of calculus states is, first off, if f of x is an antiderivative of little f of x, then the integral from a to b of little f is equal to f of b minus f of a. So what this says is that instead of doing the limit definition stuff for this definite integral, where we looked at the limit of a Riemann sum, we could instead use this notion of antiderivatives. So this fundamental theorem of calculus way is what we should really think of as the shortcut. The long way, the definition of an integral or definite integral, was all that limit stuff we did, and then the shortcut would be that we can just plug in the two numbers into our antiderivative and subtract, so always the top number goes first, and this number will give us the value of the definite integral. Okay, now there's only one little problem with this, and the problem is that we still actually have to find an antiderivative. Okay, so we have to find, we need to compute the antiderivative. And that part is the tricky part. Now, if the function is nice, then computing the antiderivatives isn't too much trouble. But in some cases, it's actually impossible to compute an antiderivative, and that really sucks if you're trying to solve one of these problems. So in situations like that, we have to play other tricks or do numeric approximations. Now, for the stuff that we'll talk about now, the functions will all be nice and everything will work out great, so there's nothing to panic about. Okay, so let's look at one quick example here. Let's look at the definite integral from 4 to 7 of 3 dx. So my function is the constant function 3, and then I'm going to integrate this thing from 4 to 7. Now, it shouldn't be too surprising here what the answer is going to be, because this is just a constant function, and so we could do a little bit of geometry to figure it out. But let's go ahead and do it with the fundamental theorem of calculus and see what we get. So the first thing that I'm going to write is the antiderivative of 3. And if x is my variable, then the antiderivative is 3x. And now I'm not going to write the constant, the plus c here. Actually, I'll go ahead and write it, and then I'll show you in the process why we actually don't need it if we're talking about definite integrals. Okay, and then I'm going to put the 4 and the 7 here with this little vertical bar. So what that means, the vertical bar, is to plug in 7, plug in 4, and then subtract the two answers. So if I do that, if I plug in the 7, I get 3 times 7 plus the mystery constant c. And then if I plug in 4, I get 3 times 4 plus the mystery constant c. And if I just compute this out, then what do we have? 21 minus 12 is, what, my brain's not working, 9. And most importantly, notice what happens to the c's. This c minus that c cancels. So you don't actually have to write the plus c because with a definite integral, because it's just going to cancel anyway. And so here, what do we get? I think we said we get 9. And if you just sketch the graph of this function or think about it, that makes sense because the width of the piece we're considering is 3, and the height is 3, and 3 times 3 is 9. Okay, so we got exactly what we should get. Okay, so here the work was figuring out the antiderivative, and the rest of it was just plugging numbers in and not botching the arithmetic. Okay, so let's look at one more example that's slightly more complicated. Let's say that we've got the integral from 1 to 4 of 9 over x squared minus 1 dx. Okay, now before we actually do the antiderivative here, we probably need to rewrite this because we've got x squared in the denominator. So let's first rewrite this as 9x to the minus 2, and that'll set us up for computing the antiderivative. X to the minus 2 minus 1, and then that's dx. Okay, so our antiderivative here will be x to the minus 2 becomes x to the minus 1 divided by minus 1. We still have the 9 in front. And then the antiderivative of 1 is x, so that part's easy. Okay, and then we need to evaluate this from 1 to 4. Now I'm going to go ahead and simplify this a little bit, and I'm going to write it as negative 9 over x because I've got x to the minus first, and the negative because, well, this negative here, and the 9 because of the 9, minus x, and then that's going to go from 1 to 4. Okay. So now that we've figured out and simplified the antiderivative, we just need to plug in the 4, plug in the 1, and subtract. And now you'll notice that there's a lot of minuses already here, so be very careful or else you'll botch it. So let's see, if I plug in the 4, then I get negative 9 over 4 minus 4. And if I plug in the 1, I get negative 9 over 1 minus 1. And then we just need to simplify this and, of course, be real careful with the negatives here because we've got a bunch of them. Okay, so first thing, why don't we simplify in each set of brackets here. In this first one, because of the 4 in this denominator there, we should probably go ahead and do a common denominator. So this will be minus 9 minus 16 all over 4. And then from that, we will take away, well, negative 9 over 1 is just negative 9, minus another one is negative 10. And so we get here 10 minus, negative 9 minus 16 is negative 25. Okay, and then if we go ahead and get a common denominator with the 10, then that would be 40 fourths. So 40 minus 25 is 15. And so we get, in this case, 15 over 4. Okay, so in this case, there were sort of two parts of it that were the meat of the work. We had the step to get the antiderivative, and that concluded, that was basically this first line here. And then we had to plug in the numbers according to the fundamental theorem and not screw up the arithmetic. So that all that stuff was the second line there, was using the fundamental theorem, so that we used it to get this step here, and then the rest of it was just the arithmetic, and then we get some sort of answer. Okay, so in class we'll talk about some more complicated examples of this, and then I mentioned at the beginning that this is actually one version of the fundamental theorem. There's another version that relates how integrals and derivatives go together. So we'll talk about those things in class, but for now, you should be in good shape.